Looks like it's after 1. I think I'll just go ahead and get started in 1 minute. Right. Today and tomorrow, we're going to have a special topic. And this special topic will also help you in a sense of being a couple of little reviews that might be helpful in your exam, some new material that might be helpful for you to pick up paper topic also. So just exposing you to brand new area of NMR. We're going to look at quadrupolar nuclei. So today I'm going to do some general background and focus mainly on the most common quadrupolar nucleus for biophysics, which is deuterium. Tomorrow, Eric Keeler, because he has some significant experience and accomplishments, going to tell you about syn systems that are so-called half-integer quadrupoles, such as oxygen-17. And there are many applications for material science as well as emerging applications for biophysics. Why are we talking about this? Well, it turns out that most of the periodic table, you can't do regular old spin without NMR. So if it's pale blue here, there's a nucleus where you can use I equals 1/2 NMR. But that's not most of the elements. That's a minority of the elements. And here with pink, there's some nucleus where it's so-called quadrupolar, which means that the angular momentum, total angular momentum quantum number is greater than 1/2. So you can see why this is more popular in material science right away. If you limit your attention to that phrase that biologists use, CHNOPS, you're mostly covered, not entirely. You got very unlucky with oxygen. But making materials, we don't restrict our attention so narrowly. So let's review some basic features here. I equals 1/2. Never quadrupole. Today we're learning about quadrupoles, and tomorrow, I equals 1/2 do have a magnetic dipole moment. I equals 1/2. All of them have just 2 levels. It's a quantized 2 levels of synthesis, and you can have the quantum mechanics. But it can be proven. It's not just an observation. It can be proven using angular momentum theory that the higher electric or magnetic multipole moments are 0. All they have is the magnetic dipole, up to very high order. Now, by contrast, there are nuclei that have I equals 0. They just don't have any angular momentum at all. It all cancels out. Of course, they lack the magnetic dipole moment, and they lack any of these interactions, and they don't have any sublevel. Okay, so that's the next simplest thing down. Hopeless for NMR. This is user-friendly for NMR. And just to review, and you know this already, some of the examples for I equals 1/2, they all are 2-level systems: proton, tritium, C13, N15, fluorine 19, P31, a handful of metals. User-friendly, but in general, you're going to see a bigger CSA than you do for the proton. That's what we've been talking about. Now, if I is greater than 1/2, that means you have more than 2 levels. That's a pretty profound difference. And maybe at the end of today, I'll just start to get into what that means to have more levels. Otherwise, we'll start with that tomorrow. It leads to more complex spin matrices and some differences in pulse sequences. The quadrupolar interaction is also a unique feature that you can expect every time you see I greater than 1.5. So if there's more levels, there's a quadrupole interaction. Two very different features, and they're both going to be homologating our line. The first thing to know about the quadrupolar interaction, I mean, quadruple just refers to what term in an expansion we're talking about. It doesn't tell you physically what we're dealing with. It's not magnetic, it's electric. It can be informative regarding bonding. For example, is the electron density near the nucleus spherically symmetric? Is it mostly S character? It is potentially much more geometrically complex even than the second rank that we learned. Even than the second. It could be higher. It can have more indices, more Euler ranks. That's where it comes. And another thing is that this interaction, because it's electric and not magnetic, can be very large in some cases. J couplings are hertz. These are megahertz, not even kilohertz, megahertz. It is not generally straightforward to anticipate which nucleus will have I greater than 1.5 and which will have I equal to 1.5. There's a nuclear shell model. It follows from the fact that protons and neutrons are fermions, which means that in the same energy level, protons will have a Pauli exclusion principle and separate the neutron flow. So they act in pairs or in teams, but separate. Protons are on, one's build-up model and neutrons on a different one. This model was developed in the 20th century in part by analogy to the Bohr model for electrons and atoms. Stephen Gapon, Maria Goettert Mayer, Hans Jensen, these are Nobel laureates, physics, Eugene Wigner, whose name's come up already in the class. So these are not easy entry kind of topics. But I can tell you a couple of things about it. There are so-called magic numbers for filled shells. Electrons have this, well, nuclei to some extent do as well. Specific counts of either protons, Z, or neutrons, and again, you count them separately, that result in exceptionally stable atomic nuclei that are binding energy due to being a complete shell. This is like noble guess. Okay, so 2 is a magic number, 8, 20, 28, 58, 200. Doubly magic nuclei. That means N is a complete shell in the, so that's helium 4, oxygen 16, calcium 40. These are particularly stable. Sometimes it's easy to understand what's going on. And I picked some examples where you might understand. So the proton, it's only got the one particle. It's going to be a spin. It just has the properties of a proton. Tritium or helium-3, you have a totally filled shell closed off, and then you add 1, it's also I equal 1/2. Helium-4 is a doubly magic state, and it's a completely filled shell, and it has I equals 0. So some of these are pretty straight. But already in the second row, we get into the things that I don't find intuitive. Okay, so helium, oxygen, and calcium, that was good, but is 6 a minor magic number? Because C12 with 6 protons, that should be capital, and 6 neutrons also has I equals 0. And what's the explanation for that? So are there like some shells that get filled up analogous to what goes on with the electrons? Is that a thing? O17 could be considered as a doubly magic number with 1 addition of a valence nucleon. However, it is not 1/2, which makes us very unlucky or lucky, depending on what you hear from Europe tomorrow. So it's kind of an I equals 5/2, which you can think of as sort of like a D state. So already in the first row, we're out of our intuition being a real straightforward thing. So we learn phenomenological rules which have nothing to do with Goetter's shell theory. It's just stuff NMR people say to each other. Even atomic numbers, Z, most abundant isotope, isn't NMR active. This is a pattern that works throughout the periodic table. But a minor one might be, if it has an odd number of neutrons, an odd mass number, it will have half integer spin. If an even number, it will have an integer spin. It's just a pattern. There's no physics that I'm implying behind that, although there may be some. Odd atomic numbers, the most abundant isotope is active. If it's an odd number of neutrons, it'll be an integer spin. If it's an even number of neutrons, it'll be a half an integer spin. So you'll find these rules work with almost no exception. So as we go up from I equals 1/2, the next simplest is a three-level system for I equals 1. I equals 1, we have several examples that there's good literature regarding deuterium, heavy hydrogen, hydrogen 2, N14, lithium 6. And then of the deuteron, just because it's hydrogen everywhere, and just because it's a really small coupling constant, you see a lot of work with it. It's in biomolecular NMR as well as in chemistry. Why are we introducing deuterons? They're trying to get rid of proton couplings. This has to do with the fact that the deuterium has a lower general magnetic ratio. It's not really because it's fluid. Deuterium spectrum is dominated by a single interaction. CFA and J are pretty small compared to the quadruple. That makes it an attractive choice for doing dynamic studies, which is, I think, where I'm going to take this conversation to by the time that I end it too. Deuterium quadruple splittings are around 100 kilohertz. And we'll look at that in more detail in a minute. That's pretty convenient and experimental. So you see a lot of dynamic studies in solid state NMR with the deuteron. So we're going to dig in on that because there's a big literature, because it's, again, the first simplest. It's just I equals 1 and it's a small value. So let's talk about the fact that there's a quadruple interaction before we talk about the implications of the three levels. I'm kind of treating them as separate topics. The idea that you have more levels and what does that do to your pulse sequences and coherences will be towards the end, maybe tomorrow. So there's another large local anisotropic term in the Hamiltonian, and it can be very informative, but also it's very, very large, and it could lead to failure of the experiment. So there's a lot of different directions this could go in terms of practical interest. But remember, it's not a magnetic interaction, it's an electric interaction. Let's look at some of its properties. So it's generally true, and it can be proven. I'm not going to get into this, but that if you have I greater than 1/2, you will have a non-spherical charge distribution that comes out of the model for the nucleus and the properties of angular momentum. So we know that we always have a monopole, electric monopole, and no magnetic monopole. We know that we always have for these cases a magnetic dipole, but there's no electric dipole. There's no electric dipole at any of the nuclei. They don't have this property. So the quadrupole is the first important electric term in the expansion. It's associated with Z itself. You would never have torque. You never care which way you were rotationally oriented. So picture that if you had I equals 0, you have a closed spherical shell, like the distribution of charge in the nucleus is perfectly spherical. Then picture that if you add one more nucleon into that shell, you could have a magnetic dipole, but you still have a spherical distribution. It's like having one s electron, like the analogy to the Bohr model or hydrogen atom. But now if you have multiple spins, multiple nucleons, multiple protons, then in that case you could have a non-spherical distribution of charge. So what would that look like? It's characterized by quantity Q, the nuclear electric quadrupole moment, as a measure of the non-spherical deformation or shape of a nucleus's charge distribution. It has units of barns, oddly enough, that's an area dimension. And that's because you take the integral of the position squared when you calculate it. Like mean square waving function. When Q is 0, that means you're spherical. When Q is less than 0, that means you're shaped like a frisbee. Q greater than 0, you're shaped like a zero. Most important thing to remember about Q is it's an invariant property of that nucleus. I don't care what chemical compound it's in. I mean, under ambient conditions of reasonable pressures and temperatures, Q is just its, like gamma, think of it like gamma, like that's just a property of that nucleus. So, if we scale this by the elementary charge, you have Q, capital Q times little q, or sometimes we say capital Q times little e for the elementary charge, that appears in the energy expression. So scaling it by an elementary charge. Another thing that comes into the Hamiltonian, the other piece, is an explanation to the question, why does this frisbee or cigar-shaped electrically charged object have a preferred rotational orientation? It has a preferred rotation orientation because of the bonds, because there's an electric field gradient in its vicinity due to the bonding electrons, especially the ones that have a little bit of S character, so they penetrate the nucleus, but they also have P character, so they're not spherically set. Most nuclei in molecules have an electric field gradient at the nucleus due to nearby charges. And it's really the very close by things, sometimes referred to as pore polarization or Sternheimer waves, really the electrons that, in fact, penetrate the nucleus or right there at the nucleus that are dominating this. Those electrons being non-spherical means you have a pore on a non-spherical nucleus and preferred rotational orientation. So the other piece to the Hamiltonian, besides Q, the quadrupole moment, is V, the electric field gradient at the nucleus, or sometimes we just call it field gradient. Now, V is a second derivative of the potential or a first derivative of the field. It's a second rank tensor because it's the second derivative with respect to the potential with respect to space. So it has two spatial derivatives, and so it's if you go to the direction where it's the largest, the steepest, that's always the z direction, and we may refer to it in the Hamiltonian as v sub z, largest spatial direction for the second derivative of the potential, or the derivative of the field. Now, the interaction energy is between a scaled nuclear quadrupole moment, EQ, and the electric field gradient. It's just that product between those two that gives you an energy. Again, throughout, E is the elementary charge. And sometimes you see the symbol Q, and Q refers to that field gradient over it. Here's the important thing to understand. When the nucleus rotates due to the electric quadrupole, it will take the magnetic observables with it. They're tied to the same substructure. And if you manage to rotate such a nucleus with your RF pulse, you are moving the electric observables around. So they are tied. Think of them as being rigidly written on the coordinates of the inner workings of the nucleus. So just like we did with the dipole, we can write the electric quadrupole moment as being an outer product of I, with spin degrees of freedom, with itself. I represent spin. It is not the magnetic spin that is interacting with, it's not the magnetic moment that's interacting with the quadrupole. But we can use it that way because it refers to the rotational orientation of the nucleus. So it's almost like we're borrowing operator that we had in our mind associated with measuring magnetic moments And now we're just using it to keep track of the rotational. Doesn't mean we're mixing electric and magnetic interactions. It's just set of coordinates, rotational coordinates for your nucleus. Okay, so our product of I represents the rotational orientation of the nucleus, and V, which is another second rank tensor, or could be higher rank, depending on the spin system, that is tied to the bonds. So just like all the other anisotropic interactions, we have a spatial piece that's tied to the molecular coordinates. We have a spin piece that's tied to the gimbal mounted kind of like rotationally free nucleus inside the molecule. Same picture as we had before. So there's the two copies of I, and there's V, and you could also, just like we do with the dipole, put V, and then the inner product of I, outer product I. We could rearrange them. But because I is not 1.5, because this is a more complicated spin system, it can be higher than second rank. So I represents the axis system for the nucleus, and V represents the axis, or is anisotropic according to the axis system of the molecule. Now the CQ is what you'll see in the literature often, nuclear quadrupole coupling constant, NQOC, or coupling strength. Or sometimes you'll see folks use it related, but it's slightly different parameter, QCC. CQ is that product that I've been talking about, EQ times V, so the magnitude of the quadrupole moment times E, representing the nuclear properties, and VZZ representing the bonding electron properties. And it will be in units of hertz if you scale it by Planck's constant. Q is constant in this, so we think of this coupling constant as being an indirect probe of our bonding orbitals happening. So if somebody says to me, oh, that compound has a really big coupling strength, and this other one has a small one, I interpret that as the statement about the symmetry, the site symmetry of that species. Like how strong is the electric gradient? And therefore, what kind of symmetry you can sitting inside in terms of its bonding. Deuterium, we're talking about it today because it has an anomalously small value for the fundamental constant at the nucleus. And for that reason, these coupling constants, which are in normal units for us and on barns or something weird, kilohertz, really refers to how big this thing is to look on your spectrum. For deuterons, it's around 100 to 200 kilohertz. Now that's big, but it's not unlimited. You're going to hear some really big numbers from Americans. So that fits inside normal digitization on a commercially available. We can measure this. I'll say more later about it's pushing the hardware to the limit, but in some ways, so we can get measurements. So it does depend on the environment. D2O's got a larger value than aliphatic CD. And if you had a strictly spherical or octahedral cycle, which you can't do for obvious reasons, for the hydrogen, you could have that like a free proton, I suppose, free deuteron plus, then we would expect it to be close to 0. And the Z direction will always be the bonding direction. And because hydrogen is almost always making only the one bond, it's going to be very close to UVX. The only thing is if you have a really strong hydrogen bond, then X and Y might be different. Picture that you're connected to, say, a nitrogen, okay, and it's the deuteron. That's axially symmetric, and nobody's talking to it in terms of non-bonded interactions, but if you put a preferential hydrogen bond protocol here, that creates for you like X versus Y situation. Now, the quadrupole Hamiltonian does not commute with the same on Hamilton. It involves raising and lowering operators, if you write it out. we'll maybe talk about this more later, or maybe not, but I'm just saying, it doesn't commute. And therefore, we can talk in terms of first order, second order terms. If you pull out pieces of this Hamiltonian that look like IZ only, and leave out the IX, IY, I plus, I minus stuff, then that's the first order term. If the coupling is really strong, first order is not good enough. We'll hear more about that tomorrow. With deuteron, we're going to say that's not such a strong coupling. 100 kilohertz is really small compared to 700 megahertz. So if I measure it on a 700, 800 megahertz instrument, first order is probably pretty good. Probably pretty good because it's so much smaller than the Xenon. So I'll just take the pieces of this that commute with the Xenon. And we can do that problem. I don't have it in my slide deck today, but we can look at that if you guys want to. Like, how do I find the part of this that commutes? I'm just going to give you the result. It's a lot like the dipole Hamiltonian. So we get something for the first order that's like IZ squared minus I times I plus 1. It's a traceless second rank, and its anisotropy looks just like all the others. Anisotropies. You both say that. So everything we said about CSA and dipole kind of works the same here, which is very cool. Now, when we use the nomenclature that I introduced before for the spin and spatial degrees of freedom, the usual convention and what's in Spiess's book is that R20, so this is the spatial piece of the Hamiltonian, R20 is ZZZ. R2 plus minus 1 is strictly 0, there's no antisymmetric term. And R2, unless you have some sort of pathological binding environment, like a helical molecule with a lot of flow in it. R2 plus or minus 2 is the eta, only if it's non-uniaxial. The asymmetry. Okay, so those are your tensor components for the first order piece only of the quadrupole interaction. And this would be traceless like the dipole, second rank. No shift to first order. No shift to first order. Again, tomorrow we'll look a little bit at what happens when you have to go to second order. But I'll just say that it exists for today. It's important only for the really strong quadrupole couplings. We really don't need to think about this for most deuterium experiments. And you can get it out of average Hamiltonian or perturbation treatment. And it will involve higher rank than just rank eligible streets. It'll have higher rank pieces. So there's the result, but we're going to look at its properties, what people use it for tomorrow. Now, a spectrum. So 3-level system. And those are levels in terms of what? What's different about this, and this, anybody? It's all I equals 1 system. This is for a deuteron. It's all I equals 1 system. But what distinguishes these 3 quasi-stationary states? Their value for what? Just think by analogy with what we did with the 2.5 system. There are 2 levels. What's the difference between the 2 levels? The orientation or the measurement of the magnetic moment along C or form, right? You try to measure that state, you're measuring how much of that angular momentum spin is along Z. So the answer to for the middle level is 0. Again, it has to be a ladder where the angular momentum changes by a magic number. So you go from 0 to +1 or 0 to -1 in terms of projection along Z. That's what those 3 levels represent. Now, what about their energies? Well, I'll just tell you something. And if you have questions about it, we can also get into this more tomorrow. I think about these levels. Tempted to ignore it. Do you want to ask a question? That's okay. Okay. If we think about these levels, this level pair is going to be at the deuteron frequency, the normal frequency you expect based on its gyro-magnetic ratio, and this transition as well. So they're both going to be in your spectral window, both of these transitions. In terms of any fine structure, like they both start out at exactly the same normal frequency. And then you're going to get these splittings based on whatever local interactions are going on. So this is just the Zeeman interaction. This is the Zeeman plus some leading terms. Now, if that leading term were chemical shield, what would happen is the shifts in the outer levels would be equal and opposite. And there will be no shift for n equals 0. So you see a shift, this one would go up by exactly the same amount that this one went down. And so they would both shift their frequency by exactly the same. So the chemical shielding, if that were the only interaction here, if we didn't have any quadrupole, these two lines would be right above each other, absolutely true. By contrast, the quadrupole coupling affects the outer state similarly. So the quadrupole coupling is like an even function of n, it goes like m squared, I squared. So it doesn't do anything to the middle level, but the outer levels both either go up or go down, and by exactly the same amount, they travel together. So it's sort of like chemical shielding looks anti-symmetric because it just has one copy of IZ in the Hamiltonian, so they both go out, one up, one down. But the quadrupole coupling, like a dipole coupling, kind of looks like an I squared term, so they will both go down or both go up. As a result, when one line shifts up, frequency the other one shifts down. And so you get a doublet, just like looks exactly like a dipole pattern in the anisotropic presentation. If you just had one orientation and you didn't have a whole powder, you just have like a slit line, just like dipole. So two subspectra, or two transitions. But we do have powders for solids, so each transition has a powder pattern, and the frequencies range according to 3/4 of QC it had, that tabulated quadrupole coupling constant QC. They range from 3/4 to -3. It's like the P2 cosair. The pink pattern splitting is reported. That means from this so-called horn to the other horn. We report that in the literature, or sometimes convert it over to a CQ. Those are the two kinds of things you see in blue. And that splitting will turn out to be 3/4 of EQP over H. Now, typical numbers, because we're going to be looking at proteins and nucleic acids, so you're going to have CH groups. If it's in a saturated environment, you expect that splitting to be about 125 kilohertz, and that corresponds to this fundamental constant being about 100. Pretty invariant. Now, I said something about this before briefly. It's demanding, this experiment. It's possible and demanding. So the perpendicular edge is useful. We don't want to just digitize out to the horns. We want to get all the way out to these perpendicular edges. You know why I'm calling them perpendicular edges? Or parallel edges, I mean. Parallel edge here, perpendicular edge here. You know why this is perpendicular in that curve? Yeah, so this is the most probable orientation, and I was happy to see Anish review that Anish reviewed this in his problem session, and then the other instructors have also talked about it. So the most probable orientation is to be perpendicular to the field, and that is this big feature here. And the least probable is to be parallel to the field, and that's the so-called shoulders and horns. Shoulders being parallel, horns being perpendicular. So we don't just want to do a good job of detecting this value. In the culture of the field, we'd like to get the full line. And that's just the standard. Gives you a lot of confidence in what you've done. So if you're going to go all the way out to the shoulders or the parallel edges, that's the better part of 200 kilohertz. And what that means is that to excite all of that, you'd like to have a 90 pulse time, 1 microsecond if possible, but definitely less than 2. And that's because of the excitation sync pattern. So in other words, 1 over the pulse width, you want it to be 500 kilohertz or so. So that you basically evenly exciting that full swan. For that, you need a really high power amplifier and a very rugged probe design. Also, if you have a high Q, you guys know what Q in a probe is, quality factor, the ability of the probe to be narrowly tuned and to really amplify the pulse that goes into it. When you want high power and short pulses, it seems like you want a good Q. However, there is no good Q without a long ring down of the pulse. So if that's a direct consequence of having a good Q. So that's not a good thing because these lines are so broad that their FIDs are very short. We don't want the pulse ringing down for a long time when we're trying to capture a signal. Typically, people use an echo detected experiment to improve matters, but it's still an issue. It's an issue of these weak, broad signals competing with or getting polluted by the strong pulse, and it's a longish tail. So sometimes people spoil the Q on their probe on purpose. Finally, the probe tuning itself has to be symmetric. So if you ever looked at your tuning on your probe as a function of frequency, like displaying that in a return loss detection scheme. The probe, it will have, like in terms of impedance, it will have a typical notch centered close to where you want to make your measurement. A good question is that symmetric? When you're starting to want to pick up signals that have a width that's comparable to the good performance width of your probe, then you have to ask if that probe tuning is symmetric and what are the properties on the sort of wings of that tuned feature. So you get into the weeds here a little bit and trying to get these line shapes perfect. I already mentioned the echo. So there's a lot for broad line, there's a lot to think about. But what I wanted to emphasize before I stop around 2 problem session, yes, please.
Why in the Q on purpose?
Yeah, so that you don't have such a long ring down, yes.
How do you do it?
Oh, well, that would be tuned differently, so there's no way to do that without having a little bit of inherent loss, like you probably end up losing performance in terms of the inherent pulse length, but you're going to go to a different combination of the inductor and the capacitor, and possibly a little bit of extra resistance even. And then you're looking for something which has a higher Q and still has very symmetric characteristics. So your in an ideal circuit, the Q is related to that combination of three numbers, the R, the L, and the C. So in there, I'm sorry, I don't have it. I'm not going to do a good job of it from the top of my head, but you can look at that combination. So they inevitably there's lossiness in that. So line shapes. The 2 transmissions don't have colors or labels on them, so you just record a line that represents the sum of the two transitions. So you get these two shoulders or parallel edges of these two horns or perpendicular edges. And no matter what the functional group is for the CD, if any kind of motion is very, very slow, we see the same Batman look, no matter where I put my neuron in our protein. But if that functional group moves and has, a characteristic hop angle, then as the temperature or the rate of the hop goes up, you can start to see some really interesting line shapes. And this, in my opinion, is the right size anisotropy to get some really dramatic window into dynamics. There's just a lot you can see, and that has been utilized in biopolymer NMR. I would say the richest literature is for lipids and what they do in their phase transitions and composition, what kinds of motions down to the methyl group at the end of the chain, on the methylenes in the middle, up near the head group. We know so much about this, and it's almost 100% from these kind of broad line. These are simulations that we did with a early student in the group, John Williams, and wrote in a review article, and they correspond to 3 scenarios. So the left column is slow, the right column is fast, 10 to the 8th, 10 to the 4th, and the column in the middle is intermediate exchange, and the actual signal intensity expected is much weaker than the left or the right. So this, if we plotted them true scale, this would be the tallest, this would be about half that height, and this would be way down in time, because there's intermediate exchange going on and lots of intensity. So we blew them up to full scale, and down here someplace that said what we would want by. But so that's slow, medium, fast, and then on the row here, we're picking different models. So the top is a methyl group, and in the middle, I believe, is the lowest one is a phenyl group, just like flip of that ring, slow limit, fast limit, and then this is the sort of thing that comes up in the middle of a lipid, where you have trans gauche or reorientation of a methyl group. And my point is that in the fast limit or the intermediate, there's a signature as to what the motion actually is. It isn't just like some order parameter or some relaxation time. It's like, oh, I know that ain't, I know what's going on. I know what the geometry is. So that's kind of satisfying. Now I'm going to use that as a way to do a quick thing here of a review of a homework problem that I think we already looked at in class. I think Anish looked at this a little bit. I looked at it a little bit. I will look at it one more time. So a motion could be much faster than the range of frequencies given by the local field, whether that's quadrupole or whether that's dipole or whether that's CSA. And you can describe it by an n-site or a Markov model, assuming that they're equally populated. Basically, the fast limit tensor is just the average. It's like time sharing between different orientations. They all are assumed to have the same fundamental interaction when rigid. But at each of the end sites, that tensor needs to be rotated appropriately to represent how it would contribute in terms of its own orientation. How would it contribute along each of the Cartesian directions? How would it contribute to each of the spherical harmonics? So one of the sites, you might have the rotation be nothing, but every other site, whether there's one other site or whether many other sites, every other site would have to have a rotation applied. And now you get a different tensor for each site, and now you just average those tensors. So there was a problem that I assigned to you to do that problem for aromatic group that has 2-site flipping, or a methyl carbon in a T-butyl group where the methyl groups in that T-butyl are changing places. So those correspond exactly to the top and the bottom here in terms of the geometry. That's a 3-site hop like the T-butyl, and that's a 2-site flip like the phenyl. So now you've seen an interbutyl. It has to look like that in the fast limit, right? For the deuteron, just to pursue this a little bit more, the principal axis system, we have values for the different components of the spatial tensor, 2, 0, the 2 plus or minus 1, and the 2, 2 that we discussed a few minutes ago. So 2, 0 is just delta like it is for the CSA, and in particular is VZZ with those weird units of bonds. V2 plus or minus 1 is expected to be 0, except in some pathological bond case. R2 plus or minus 2 is your asymmetry parameter scaling. That's a width. Now, VZZ, I didn't remind you, we said it's already, that's a component of the electric field gradient tensor and along Z, the maximum. It's related to QCC by this equation. So we're supposed to use VZZ, but it's related to a famous thing with normal units. And so I suggest instead of R20 being delta, let's work with R20 scaled by EQ, so we get something with some kilohertz units. I don't like talking about 10 to the 21 per meter square. So we're gonna with all due respect to Hans Spies, we're gonna just use a different spatial. It's like taking part of that C constant in front of our Hamiltonian and shoving it into the space. But for us to do this rotational average, we need to know some geometry, right? So if this is a CD3 group and it's rotating, what's our rotor axis? Could be the bisector, but a more convenient way might be to refer to the bomb. So the RC bomb. Okay. And what is the unique axis for each of the neurons? So we have 3 different sites for the neuron, and what is its unique axis or its static? Easy. If it didn't rotate, if you froze that metal out like a 2 degrees Kelvin, it doesn't even work to go to 100 K, by the way. I still believe it. But if you go to 2, they probably stop. I don't know. No, they tunnel. Some of them tunnel. But let's just pretend we can freeze them, if we know how to freeze. So what would the PAS, that's the V axis for the PAS? The bomb. Yeah, the CD bomb. Okay. So we know enough about the geometry to do this problem. We just have to think about how we want to do it. So the rotation axis is the RC bond, the unique axis is CD bond. But how do we calculate this average? What are we really going to do? Anybody have any thoughts? We're going to use this equation, right? We're going to assume that they're equally populated, so we're not doing any population weighting. Each site has the same value for the PAS frame, EQ, VZZ. Each neuron site has its own direction, though, so we need to relate each site to a common molecule big spread. But if we want to compare them, we can't do it in the 3 frames. We have to put them all into one common frame. And one thing about these problems is picking the right frame to combine them. Yeah. I mean, you can get lucky or unlucky. What frame do you guys want to use? Yeah, you want to put them all in this rotor frame. Yeah, that's what I want to do too. So a specific neuron occupies each of the 3 sites equally, so we want an expression for each of these, but we need to rotate all 3 of them onto this beam. That's going to be our molecular fixed frame, the rotor frame. But you could pick something else, and I don't know if you would be as lucky. We'll see. So what are the rotations? If I have to go from PAS, site 0 here, to this, what do I need to do? How do I rotate that? I have to do all 3 of them, but let's just start with this one that I'm calling site 0. What are the Euler angles to get me from that being Z to that being Z? Just knowing what you know about molecular bonding.
Yeah.
Yeah, you're going to have some Y, and since it's uniaxial, we pretend it doesn't matter, but actually, in reality, you already use the mutual perpendicular called the node line. But yeah, we're just going to rotate around Y by how many degrees? 109.5. That's the first step. But now if I needed to do these other two, what else do I have to do? And the second operation I have to do. So this is the trick. Why don't you break it down into two steps? PAS to NAF, or site 1 or site 0, just picking one of them, is Euler angles, and you just said it. Y is 109.5, so it's going to be 0, 109.5, 0. But there's another step for these two guys, which is that you need to then rotate them. While this is Z, you need to rotate them around Z by 1. Okay? The trick was to consider convenient frame and then to break it down into the two steps. One last trick is that we're allowed to do that as one set of Euler angles because there were so many zeros. If we do it as two sets, we're going to be figuring algebra for a long time. So PAS to MFF is 0, 109.50, and then if you're converting the two sites when you're sitting in this nice MFF, is 0, 0, 120, 0, 0, 0, or 0, 0, minus. Okay, so because of all these zeros, I can combine. Say PAS to MFF 0 is this, 0, 109.50, PAS to MFF 1. So site 1 is then molecular frame is 0, 109.5, 120. And then to site 2, it's 0, 109.5 minus 120. And I'm noticing that I can just say the nth site, and it will be n times 120. So I have a set of Euler angles to get site 0, 1. Yeah.
What do you mean? We go back, what do you mean by your n times?
N times 120 degrees. So site number 0, 1, and 2. Those are the three sites that go around 96. Yeah, thank you, Roger.
The angle will be 4 sides.
Yeah. Yeah. You can just keep going, right? But you don't need 4 sides, but yeah, here. And then I'm just going to plug those angles into this kind of thing. And I notice that this is an L equals 2 second rank tensor. It's a uniaxial interaction. So I only need one rotation the way we set it up. And in the PAS, I only need my n equals 0 term. But in the molecular fixed frame, I don't know. This is the lab frame. I might need to be better. I just don't know. So I could have all of these terms. So I need to calculate them all, sadly. And I'm going to use this that we had already in another plan. Okay. Now, if I'm going to be doing the m equals 0 first, at the next slide, yeah, there. If I want to do m equals 0 term, I'm going to have something like this. Either the I, M, and then alpha had this value, and then D2 M0 beta has this value, and then this is the PAS value. Now, D2, if M equals 0, that's the 0, 0 term, I need to use I, and I is our friend PG goes to. So I just have to plug all that stuff in. And lo and behold, I get exactly 1/3 of the static value. So again, I'm only calculating in this slide the m equals 0 term. So this is a general expression. This is for the m equals 0 in the molecular frame. For any site, the n dependence falls out because n equals 0 and n only shows up in that exponent for that Z rotation. So the n dependence goes away, and so for all 3 sites, you just get the same answer, which is plug it into P2 plus theta, it has to be 1/3, right? Now I also have to do the m equals 1 term. It's not quite as simple, but it does simplify. So if I put m equals plus or minus 1 instead of m equals 0, 2 things change. This is no longer e to the 0, this is e to something. And I also have to pick a different term from down here. I need a term that relates 1 and -1 to 0. So I look here and I see that that is either G or minus G. And so filling all that in, I put 1. Actually, that should say plus or minus 1 like it does over here. I'm missing this symbol here. And then G looks like this, but I could have plus or minus of that also, for the plus or minus 1 term. So we end up with something that looks like this, e to the plus or minus I. And then alpha is n times 120. So I can plug it in and I can get the right expression for each of the places. Notice that this kind of projection factor has a value that's n independent. What am I going to do with this stuff here? Do you remember what we did with it before for another problem? We have 2 terms, one for the +1 and one for the -1. So we ended up with e to the I times an argument, depending on which site we're on, and minus e to the minus I to that argument. Do you remember what we had to do with these? We recognize them as being something. We just converted them to cosine and sine. So this is like 1 minus 1 to the 0, so nobody cares. But on this one, it's not obvious it's going to come out to be 0, so we convert it to being 2 times the sine of the same angle. Funny thing happened though, is that when I go from the n equals 1 to the n equals 2, I get the same answer except the opposite sign. So that's saying in the average tensor prime, right? So we have the bond axis. If I say in that frame, what is the 0 component? In other words, the major component of this tensor, I get a third of whatever it was when it was the static value. But if I'm starting to ask for the n equals plus or minus 1 values, they average to 0 between them. So there's no anti-symmetric part. And I'm not going to go through it in as much detail, but the same thing happens to the n equals 2 term. It all cancels out. So on the averaging, those asymmetric or anti-symmetric terms cancel to 0. The n equals 0, uniaxial piece survives, is n independent and has this stuff. So this is like your last review of a problem we've seen a couple of times now for a dipole on CSA. And it's the basis of those wonderful line shapes. Relaxation experiments, whole burning experiments, there are lots and lots of things people do with deuterons to probe motion. It isn't just a question of probing line shapes. And in the deck, which we'll post later today, there's some nice little examples of doing a hole burning and watching that hole migrate to other parts of the tensor so that you can see the rate constant at which slow processes happen. I think I have a beautiful, beautiful experiment from Hans Speetz's lab where you do a similar thing except that it's 2D. So you ask if you have chemical exchange, if you start here in the tensor, where might you end up after some mixing time? You get these lucid looking figures that are just so informative and so beautiful. T1 and T1 anisotropy, the turning or crossing zero crossing points of some of these deuterium relaxation gives you lots of the anisotropic features, and experiments like that have even been applied to proteins. This is a loop of a glycolytic enzyme. And the last thing I'm going to show you just as a phenomenology here is that because it's so much like the CSA and the dipole coupling, it was expected that it would respond the same way to MAS on this theory. And some of the first work of the kind were done by Bob Gold, who's a real hero of the deuterium NMR literature, looking at MAS line shapes and showing that they're actually even more informative than corresponding static line shapes. So this is a whole paper that I'm citing here. So there's a lot that people do with neurons and biophysics, and it's not always. Not always, just because they want to study motion. Remind you again that sometimes it's substituted because you do a solution NMR and that's your field block and your shift preference and your solvent suppression sort of thing. Sometimes we're deuterating just to get rid of those protons and to get narrow line. Sometimes we're deuterating to do HG exchange. Sometimes we're trying to edit out domains or annoying interactions. So there's lots of reasons people put deuterons in, but obviously my favorite is to talk about them and promotion. So I'm going to stop at this point. And maybe tomorrow, if that's okay with Eric, I'll start by just saying a little bit about the level system and how the whole sequences are different. And then, yeah. So, but give you a qualitative feeling for what it means across the average ones, okay? So we're gonna take a little break, and then Anisha's gonna look at some homework problems with you. Yeah. Yeah.
I'm going to take another 5 minutes to set things up for today. Great. No, that will happen at the end of the semester. Okay. Just while I set things up, we can see in progress. Today's outlook for the next three problem session will be the end of the semester included today. So today we're going to discuss the problem set on solution and relaxation. The thing has been posted, so I strongly recommend that you. I don't know if you have attempted solving it so far, but you'll find that trying to solve that first will help you tackle the exam in a very reliable manner. We'll go over that today. Next week, we will come back to what we started last week, which is the average Hamiltonian calculation for the RDR pulse sequence, the general approach for AHT, and finally, we will come to the demo session on the analytical software. I suspect you have 10 days starting when I post it. Not imagine more than that. So I have some info. Yeah. Really. No. Still purifying code. And then with that, so that's some data from the past. So what's so should I step in and army which didn't and so it was like I'm sure I was like I was very poor. I didn't know how I was going to do that. It's not so this is quite easy. So it's, yeah, so now yeah, this is I feel like right, exactly. That's what I yes, the first year so much time to explain it back up. Yeah, good. Yeah. So, how long is the video? And exactly, yeah, it's the same for us, but it's like 30 minutes. 30 minutes. To so it's like just talking and so yeah, it's already probably okay. Joshua, I said that when I were thank for going here. I need to write that last years. I went in my back in my undergrad. It was so much fun. Very, very fast. I see the ocean. Listen. Yeah. It was really upset. Music. proposal kind of way. I slowly did it for March 6th. And then I said, it's okay. But I mean, what do you do? I don't think you do everything, like, no. To networks is good. That's okay. This is, I guess, 15th Street. Like, wait, so each also will be, yeah, there's something for you. Okay. Yeah. Yeah, that's crazy fast. That's the main fun. Like you see, with the details, and you will have a. Somewhere, very fun somewhere. Okay. I wish we had more time to discuss this problem effects, but we have only one session. We try to make it as much as possible. If you look at this problem set, it's quite long, as you might have noticed. And I'm going to pick out a few of these to discuss in class. Some of these are very complicated problems as well, in not which I solutions to do. But for the yeah. Okay. We should do a brief refresher on like relaxation as a sort of generally speaking, like before we could review some of college and everything. As you would like for the topics and other subjects, so relaxation feels like it's a review mirror. So in class, we have discussed the experiments involved in the measurement of relaxation for inverse recovery for T1. So, an example, so this is experiment where you knock the magnet down with 180, hold for some period, waiting for it to recover towards front, that is a 90 pulse to measure the intensity, and that gives you a curve like this, which is inverse recovery curve. Then we talked about non-echo, this is T over 2, 180 T over 2, which is essentially refocusing chemical shift evolution to see how much transfer coherence is lost to T2 relaxation. And then we finally talked about some of these examples where we said that the instantaneous magnetic field of the field is given by the sum of the static Z field and this local fluctuating field, and this local fluctuating field in turn comes from fluctuation in the orientation of the molecule relative to the static magnetic field. So, the orientation is changing. For example, if it is an NH, the NH bond vector orientation relative to Z is changing, and that changes the instantaneous frequency by virtue of the orientation dependent dipole coupling, and similarly for chemistry. This gives you the local fluctuation of the magnetic field, which is then broken down into the isotropic and anisotropic part. Isotropic part is a time independent average. So you can sort of break that into an H0 term, and the anisotropic parts can be broken down into a longitudinal component and a transverse component. That should get rid of this. And then we said that at least in the limit or in a specific situation where you consider what is going to be described as adiabatic relaxation. I can simplify this Hamiltonian. So this is the time-dependent instantaneous frequency from the chemical shift anisotropy. It has this longitudinal component and two transverse components. That this is representing that decomposition, and then we can sort of rewrite this frequency curve. So by now, I hope we recognize these terms in the CSA Hamiltonian. Right, so gamma delta sigma is the frequency, the CSA or gamma delta sigma V naught is the CSA in kilohertz of frequency term, because here we should recognize gamma V naught is the frequency, the omega naught lambda frequency, and delta sigma is representing in ppm your chemical anisotropy itself. And here, as we were just discussing, y2 0, y2 minus 1, and y2 plus 1 are the corresponding spherical harmonics that describe the orientation of the molecule, or describe the frequency contribution of the orientation. The orientation itself is given by capital omega of t. Any guesses what capital omega of t is?
Hello.
Yes.
Yeah. Can you zoom into the whiteboard? I can't see it.
I see what's happening. Okay. I'm just referring to the slides here, not using
Yeah, thank you.
Thank you for pointing that out. Yeah. Yes. What is capital omega of t? More generally, the Euler angles that describe the orientation of the principal axis of the CSA tensor relative to static magnetic field. For uniaxial CSA tensor, phi becomes irrelevant generally, because you don't have, it doesn't matter how you orient the CSA in static magnetic field. But if the CSA is non-uniaxial, then you have to involve both the angles in the calculation of this spherical harmonic. And broadly, you can sort of imagine that because this is a time-dependent fluctuating orientation, it's fluctuating frequency, so you can define its average and variance. Its average is 0 because the molecule samples all orientations with equal probability. Therefore, the isotropic average of the CSA is 0. But its variance is not. That is where relaxation arises from. This is just an expression for all the spherical harmonics and the mathematics of all that stuff. We're going to talk about mainly this for today's problem session, which is adiabatic transverse relaxation. The conceptualization of that, and then we go to the formula for calculating adiabatic T2, is that, like we said, the anisotropic frequency has a sort of transverse component, so fluctuations in the xy plane and fluctuations in z along the static magnetic field. When you fluctuate the field in z, you are changing the energy spacing between phi and phi, right? And the energy spacing is directly related to the frequency of precession, right? So, because E is equal to h bar omega, and omega is the frequency in the energy gap in frequency terms, so if I create transverse coherence, it will precess at that omega. If I fluctuate this energy spacing, the precession frequency is also fluctuating with time. And this causes individual spins with the sample to eventually lose phase coherence relative to each other, because they all sample random fluctuations in the energy spacing as sine coherence. Does this make sense? So you start off with complete phase coherence after a 90-degree pulse. So 90-degree pulse knocks the magnetization from Boltzmann equilibrium over the transverse plane, and that is a phase coherence. The density matrix with non-zero term will be off diagonal. And that phase coherence is eventually lost because these spins evolve or presets with slightly different random frequencies. And the average of that over time eventually disappears, so you get no phase coherence here. So that is adiabatic transverse realization. If you go back to yes,
Just hold the average for all set. The average on 87.
no, because you're doing this for every individual field. Instead of averaging over the frequency itself, you're averaging over e to the I. Frequency. That's where the phase power comes from. So that the way that it goes to zero, phase coherence eventually goes to zero. The way that it does that is equilibrization. If you remember the BWR theory that you were studying on red field theory more generally, broadly speaking, that had, if you have, for example, the CSA mechanism, it has two terms in the T2. One is the spectral density at zero frequency, and the other is spectral density at the lambda frequency. Which of those two terms is the adiabatic T2? Zero. Right. So J of zero, particularly zero frequency, is the adiabatic T2 relaxation, and the other is the non-adiabatic. It is spectral density at the lambda frequency. That is happening because you have fluctuations in the transverse lane. The field instantaneous field experience the transverse lane. And that is going to cause spin flips. And in order to trigger a spin flip, you need to apply a pulse which is resonant at the lambda frequency, which is why you get spectral density at the lambda frequency. Yes.
So, the way I'm visualizing this in my mind is that there is a fluctuation, and this fluctuation have different frequencies, right? Like this fluctuation is, you can decompose into like a lot of different frequencies, and eventually the frequency that has like omega naught that matches the frequency, right? Omega naught. If one of the component of this fluctuation in frequencies have omega naught, that will be exciting, right? So how do you visualize this? Like, what's your opinion? How do you visualize it? Am I understanding?
Yeah. So the way in which we think about this is J of omega is the term that you're trying to understand. And what is J itself? Spectral density itself, it's one-sided Fourier transform of the correlation function. Correlation function itself is coming from the tumbling motion of the molecule. Right? All of this relaxation, at least for the solution NMR, is coming from tumbling. The overall isotropic rotation of the molecule. That's what we summarize in some. Now, if when you say Fourier transform of the correlation function, you're asking, I got zoom. Why do this load radius? Keep discussing because I'm not pointing at anything on the board. If the molecular motion has this substantial frequency component at the lambda frequency, and that's what you're doing because this is a random stochastic process. It's not a sinusoid. It's a Fourier transform of a sinusoid would have one frequency. But the correlation function, which is exponentially decaying, is going to have a distribution of frequencies. So what we're saying is this overall rotation motion, which is described as someday, has a certain frequency component at the lambda frequency. So the instantaneous field along x or along y it's fluctuating at a frequency close to the normal frequency. And when it does that, it acts like a 90 pulse, which causes the transition, spin up to spin down, or vice versa. That is where non-adiabatic. It's non-adiabatic because you've done a frequency flip, you've done a flip, you've done exchange energy with the environment. That's why it's non-adiabatic frequency transition. That's the intuition for. Okay, I'm back. Huh. Where am I going? Oh,
No, use the share screen.
no, I'm getting kicked out of the Zoom meeting.
Internet is.
I'm using the same Wi-Fi. Everybody. If I stop the screen share. Just to complete what I was saying about non-adiabatic transition, for dipole coupling mechanism, you will see some frequency and different frequency. Also, you will see J of omega n plus omega h, J of omega n minus omega h, and even J of omega h if you're looking at nitrogen transition. And that's because you could have, for the dipole coupling mechanism, you could have flip-flop transitions, flip-flip transition, and even transition for the partner fit alone. Which could trigger your relaxation and it will create relaxation. So nothing's going wrong.
So like for the double quantum transition, we think of sum of frequency, right? Is there a case where that double quantum transition is rather a difference of frequency instead of being the sum of it?
Not about the time. Most obviously fine, but some of frequency. Something is good.
Should I get the directions? Just patiently waiting for us on
Sorry,
here.
sorry.
Ready to know? That's okay?
Yeah. I think it's fine now. Because I got kicked out of the Zoom. Okay,
You got kicked out of Zoom?
Yeah. A couple of times.
Okay.
But now I think I'm in there. And now it should be okay.
Where
I want the same Wi-Fi that I need. I'm on public. So
Yeah.
it'll be fine, right?
Yeah.
So far, so good.
Okay.
Thanks.
Are you plugged in your laptop? It's plugged in,
Power.
right? Yeah, power.
This is an important slide that I also want to review. Fluctuations in the transverse field will drive both T1 and T2 relaxation. The T1 relaxation is necessarily non-adiabatic in the terminology that we will be using. Fluctuations in the longitudinal field will drive T2, in specific adiabatic T2. And for today's problem session, I'm going to mainly focus on adiabatic T2. You can go back and sort of solve the same problems using that field and visit the same subject. Okay, so after this, our slides discuss in great detail what the random phase model characteristics are, and you do all of this. We come to a very important result, which are thus you may consider that way. R2, adiabatic R2 is variance times correlation. Variance in frequency times correlation. Remember, the average delta omega is 0, the variance is non-zero. And that is what contributes to R2. The important thing is to use this result to sort of build connections between the underlying anisotropic Hamiltonian and the R2 that you expect out of it. So this, for example, is we took the CHA Hamiltonian with all three components, IZ, I plus, and I minus. We pulled out only the IZ part and used the random phase model to get variance type correlation, right? If you use this, at delta omega, the instantaneous varying frequency is given by this expression. And you get this for the correlation type, and from a bunch of algebra tells you that this is what that variance is. So 4 over 45, which is a constant that comes out of doing the math, but you get omega naught squared delta sigma squared. Right? So here, omega naught is gamma b naught. I hope you see that. Omega naught delta sigma. That is your instantaneous fluctuation in frequency because of the time varying orientation of the molecule relative to the magnetic field, and that gets squared to become the variance in frequency. Remember, this result is quite general. So now what we're going to do is step away from anisotropy, come back to it later in the session, and talk about the fluctuation in the isotropic television and see how that can drive relaxation through a mechanism that we typically call chemical exchange. Am I still on Zoom? Okay, so problem 1 says, this problem says, use this expression, R2 equals variance times correlation time. To derive an expression for R2, view through chemical exchange in the fast limit. Assume the equilibrium populations of sites A and B are PA and PB. Chemical shift are omega A and omega B. And tau C is equal to 1 over KBX. Tau C, of course, is just a number that we put into the generalization, which we will do when we go to problem 3. How do you get that variance? You have problem 1, PA, omega A, PB, omega B. And you have this chemical exchange.
Variance is like deviation from the mean value.
Right.
So
Mean square.
yes, so can just omega minus, and then omega 2 minus the shift.
Okay, so mean chemical shift. What is the mean chemical shift? Remember, this is saying fast slip. So KEX is necessarily much greater than omega A minus omega P. What is from the steady state. So the mean chemical shift is then how much does A deviate from the mean?
Oh, shit.
That's right. Rejections, contradictions. There are no objections. 1 minus PA is P. I get this. Yes. And I'm going to just generally define this as just delta. Delta small. Delta small omega is omega A minus omega P. I don't know if the problem defines it the other way. Okay, it does not say. Alright, so then in that case, what do you get for delta omega B? Simple enough. In which case, what is the variance?
Square first, then add, yes.
Yes, sorry.
I'm getting weird looks for this, but yeah. Okay. I don't know why that happened. This turns out this is a little loose sometimes. Remember, we're taking again like this is the fluctuation in
shift in field for omega for site A, and this is the fluctuation for site B. Those two themselves have to be weighted by the population. Like, yeah, does that make sense? So you, instead of what we used to say, you because each term has a weightage of the field. And what we did would have been, of course, true if you had half and half. But you have to weight each side by its relative population in that square. Because variance again is mean square deviation. So delta omega squared is square deviation. And when you take mean square deviation, you weight it by the corresponding probability in order to get the variance.
Not by p squared, just by p.
Or generally, fluctuation squared. Okay. Xi minus x bar. And then the square root becomes standard deviation. In general, weighted by the population. Okay, what does that mean? Yes? We're setting the same thing again. For the first term, I get PA times CB squared. The second term, I get PB times PA squared. So can I take out common? Yes. Right? That center is 1. R2 we said was variance times correlation time. So you get this very famous result of chemical exchange R2. PA to be omega squared KTA. If you are studying chemical exchange in the past, this becomes a very handy expression that you will use again and again. For adiabatic R2, because of chemical exchange. Any questions on this calculation? This expression is what will dictate whether or not certain exchange phenomena is observable under a given set of conditions. The problem 2, which we won't do right now, but very insightful, will tell you, let's suppose an exchange running of 1 per second can be detected experimentally. And these are like experimental depth rates. What is the highest R2 that can be measured and what is the lowest exchange R2 that can be measured? And so it says, suppose you can detect 1 per second. And if it is the first minute, what is the smallest population of the site V that we will detect the line broad curve? Greater the difference in chemical shift, smaller the population of CV that you will be able to detect for the same R2. Yes.
This will also depend on the other install population. Your intensity is also lower in the site noise, but you have a solar peak server.
Oh, remember this fast element. So your peak is always, I mean, when you have a very skewed population, your peak is essentially at the like 99.1, what you see in your group, for example, mostly towards the major peak. Then you have 1% or 2% for minor peak.
log of 16. Okay, let's talk about problem 3. It's also very insightful. It applies this two-stage jump process that we just discussed involving chemical exchange to protein folding. And suppose an alpha carbon has a helical conformation with a population of 0.95, but randomly unfolds to random coil population of 0.05. Okay, so then let's set up the problem. Kind of straightforward once we've done this. Those are the populations that we have. Then it tells you secondary chemical shift, which is the difference in chemical shift between the helix conformation and the random coil conformation is 3 ppm. If the unfolding rate constant is 500 per second, unfolding in about 2 milliseconds, what do you predict for R2 at a proton Larmor frequency of 600 megahertz? This omega helix minus omega random coil. 3 ppm. And remember, we're doing carbon. Just like omega. Proton Larmor frequency is 600. Approximately, what is the carbon Larmor frequency? Just to have this memorized for the rest of this class and I guess.
I think it's an embarrassing tattoo. That's not something for attention. So what's the answer?
150.
Yeah, it's a quarter, nitrogen is a tenth. Carbon is a quarter.
Remembering those two is very helpful. Okay, so carbon Larmor frequency is 150 nanometers. This is the difference in chemical shift between the main state and the minor state in ppm. What is it in kilograms?
One point. Yeah.
It's nuclear. I tell you this difference in chemical shift, helix minus random coil is 3 ppm. And these are your Larmor frequency. What did I start off by telling you this nuclear state? Yes, pardon? Carbon. When you want to tell a carbon chemical shift difference in ppm, kilohertz would be multiplied by
150.
Hertz.
carbon Larmor. This side is
Times 10 to the negative 6 times 1 times 10 to the 6. 4.
450 hertz.
That's too pi or not?
Yeah, we put that in. That is 450 hertz. Okay, now let's do some chemical kinetics. The problem says unfolding rate is 500 per second. The formula we have says KEX, exchange rate. How do you get exchange rate out of the unfolding rate?
Folding plus unfolding.
Right. So how do you get folding rate? Right. It's a period balance. This is say the folded state, we can define as A. The unfolded state is defined as B. This is the rate constant of unfolding, and this is the rate constant of folding. So, This must satisfy what?
Populations.
U over F, U over F or F over? F over U, we got one answer. This changes everything. Forward rate divided by backward rate. Is it product over reactant in the angle of reaction chemistry? Or is it reactant over product? This is U over F. What is that ratio? These numbers, the A is 0.95, the A being the folded state, and B being the unfolded state. So this is just 5 over 95, right? Makes sense? I did 0.05 divided by 0.1. 5 over 95. Folding rate is almost anyhow. Folding reaction is sub-millisecond. So from that, AEX is AU plus KF, which is equal to so 10 to the 4 per second. Now I pose the question: is this exchange in fast? Is this unfolding process, folding, reversible folding, unfolding process? Is it in fast exchange relative to the carbon isotopic exchange? Why?
Very fast. If you compare the frequency, which is what did we give for the transmission?
You got this.
Yeah, so 450 hertz versus the other one is 10,000 per second, right? That's 10,000 hertz, 1 kilohertz.
One is in hertz, the other is in second, per second.
Per second, isn't that hertz?
Hertz is cycles per second. If you've got a cycle, what do you account for that? 2 pi. So I have to multiply the emission difference by 2 pi. And this is really important in determining whether exchange is fast, slow, and lean. Do not forget to account for the factor of 2 pi. And if I do the calculation, you will find that it's so this is approximately 2827. Still almost an order of magnitude faster. So fast exchange still true, and we can use the formula that we had. So PA and PB are 0.95 and 0.05. Delta omega squared is, remember this number, 2827. Well, not 450 squared. And KEX will come out with 10 to the 4. And if you do this calculation, you should get 38%. So now, at this stage, you have to put in the numbers in. figure out the right answer. But that's the process by which we arrive at this answer makes sense. These are the critical stages where you might stumble. So remember to use the Larmor frequency for the correct nucleus, depending on which nucleus you're studying and exchange of. And remember to convert that frequency difference in per second or radians per second, which is what is the comparable unit with rate comes the physical, physical chemical measure. Yes.
You're wrong. Okay. We're going pretty sure that we did. Really? Concentration of use.
Here, this ratio you are saying to use 12 over x squared. First order reaction.
So what we are saying is that because of the exchange, right? Just because of the exchange, you see some go
Yeah.
Okay. If you will.
That is the in this intermediate to fast limit. Well, the experiments that you can use to measure that are to exchange are many. We discussed many of those in class. We showed you how you can vary the temperature. And you vary temperature both population and rate constant will change. And you will see a difference in line width. So this is line shape analysis. And you can see how the line will change in function of temperature. You can relate that to R2, and with that you can get the rate constant for 48 or 48. But of course, art is discussed also more involved liquid expressions. In this case, we would use probably you could use something like a CPMG experiment, which is a train of 180-degree pulses. As you change the interval at which you apply these 180-degree pulses, you will see a suppression of the exchange contribution, which you can then fit to get that exchange on 2. There's also a problem in this problem set on calculating what that train of 180 pulses will do when you do the CPMG experiment. We won't do this, we won't do it today. It's a very informative experiment, and we see lots and lots of bits of experiments like CPMG, relaxation of the relaxation of the detect phenomena of this spectrum. Okay, so that was problem 3. The next one I'm going to do is an interesting one. That is problem 12 in this problem set. And that was those were the problems on chemical exchange. That is how the fluctuation in the isotopic chemical shifts between two conformations of a molecule can drive relaxation. Okay. Now we come back to what we were discussing, which is fluctuation in the anisotropic frequency because of change in orientation relative to static magnetic field. This problem 12, is long text. Cross correlation between the CSA Hamiltonians of two different nuclear spins can constitute a relaxation mechanism. Calculate the relaxation rate constant for zero quantum and for double quantum problems. And it's important to do this using both the random phase and the red field theory approach. I'll do the random phase approach in class, and then go back and apply it using red field theory. Whether a particular relaxation pathway is regarded as auto or cross dependently operated basis, matrix equation for relaxation of those two. Using these results, transform this to obtain an equation for relaxation of XX and YY. And what do you conclude? So this is sort of an open-ended problem. It goes into a lot of different sufficiently complicated fields. But we start with the very first state. Calculate the relaxation rate for zero and double quantum coherences using the random phase approach. So in this problem, we've got a spin I and a spin S. I don't know if what, yeah, okay, spin I and a spin S. Assume that this nucleus has a certain CSA and this also has a certain CSA. And then assume that there is an IS dipole coupling and then an IS scalar coupling. For this problem, I'm going to ignore the IS dipole coupling and only focus on the chemical shift dynamics of the two spheres for simplicity. In class, for example, in the notes, we saw that the Hamiltonian, the anisotropic Hamiltonian in the longitudinal component is given as this. Right? So y20 of capital omega, where omega is the orientation of the principal axis of the CSA tensor. And then this gamma delta sigma B naught. So for each individual spin, what are all the things that will be different for I and S in this expression for time dependent Hamiltonian? You have 2/3 gamma delta sigma B naught y20 of capital omega of C times IZ. Which of these terms will be different for I and S? The gamma will be different? Yes. Gyromagnetic ratio of nitrogen proton. Delta sigma? One yes. Yes, Krishna?
Yeah, I think so.
We all think that the chemical shift dynamics of nitrogen and proton is not different. Is B not different? No, fortunately. B naught is not different. So, those two simply. Y20 of capital omega. Y20 is a function of spherical harmonic. The variable inside it is omega of C. Is omega different? This is a non-trivial question. Right. So the principal axis of the N15 PSA and the proton PSA may not be collinear. And if they are not collinear, then you don't have the same orientation. Relative to B naught, so you don't have the same Euler angle going into that expression. Does this make sense? But for simplicity, I'm going to assume that the N15 and proton CSAs are collinear. I don't actually know if it's. Oh, well, yes, I think that is the dipole. I'm talking N15 CSA and proton CSA. And also the proton CSA along the bond.
They are each off of the bond by some small angle, but I don't think it's a coincidence where they're off in the same direction.
I see. Okay. So maybe the error will add up in this case, as opposed to subtracting. Okay, but here I have to account for gamma I, delta sigma I, and IZ. Similarly, for S, I'm going to just write all of this as just CI. Use of CS. Here CI is, I can just consume the full current. Right, so rigorously you would consider the fact that the two tensors don't have the same orientation, but
You don't have the same orientation, do you again do the rotation and try to align them together, like the axis?
yeah, I mean, you sit in the and then you then have to set up nested rotations inside the y20. So then it's a spherical harmonic or spherical harmonic. A general nested sort of expression will have to pop up, but you can try and guess you would project along one and go from there. But then you would have extra terms. They're not predicted. Okay. So the total anisotropic time dependent frequency. Remember, I picked out in this formulation the isotropic dynamic shift has been bunched with the Zeeman handle. That becomes the time independent. Or and I've neglected the dipole field. You can, if you want, you can also remove the scalar coupling with the range. All of that becomes time independent. Zeeman, chemical shift terms, scalar coupling. And then you have VCS later. Dipole coupling is ignored for. Okay, so if you add up these terms, you get CI like Z plus CS SV. These remember are operators. The question is asking you for the relaxation rate constant for the W1 protocol, whose expression is something like it's plus minus sign. So the sum of the flip-flop or flip terms. And the sum of the flip-flop terms plus minus and minus plus that becomes zero quantum coefficient. Now, when you just had this CIIZ, you were able to get T2 relaxation for I plus and I minus. Right? For just I plus, I minus, you just did CI squared times the correlation. Right? Because CI, remember, carries the fluctuation in frequency, which is this. Delta sigma omega naught. And you squared that and multiplied that by the correlation time to get R2. Right? So gamma delta sigma B naught is the fluctuation in frequency. This Y20, this orientation dependent term goes into this correlation time, and that for the rotational diffusion of the sphere takes on this value. And that leads you to this. So variance times correlation time, where variance is a constant number 4/45 or whatever, times delta sigma omega squared. Let me for simplicity write this as so you have delta sigma omega here, and you square it to get the variance times the correlation time with a sort of a constant that is carried over. What do you do for the double and zero quantum coherence? How do you figure out what is the fluctuation in frequency for the double quantum coherence and the fluctuation in frequency for the zero quantum coherence?
I'm remembering something from our last lecture where you multiply each of these spin angular momentum with the other one. So like maybe IZ times the identity.
Right. That's where we have to go. The identity is equal to what?
I don't know plus side data. 1 no, just side data. Okay.
Actually, I'm not sure. It looks like I forgot. But remember, when we do IC times identity part comes from the S space, S subspace. The I is already alpha minus beta, and identity is for the S subspace.
Oh, yeah.
That is then something like that.
Oh, IC is 1/2 I alpha minus I beta.
That is correct. I don't remember if that also happens for the identity. I don't think so. Yeah, it shouldn't. You just have one. I don't know stuff. All right. Alpha is alpha. Alpha is beta. I beta is alpha. Beta, beta. What do you do with the other term?
1/2.
I'm just using this notation to denote which subspace you have to apply the identity operator to. This is alpha plus beta. Let's drop the heads if we need it. The only difference is these split up alpha beta terms have opposite signs, but it's plus here and minus here. Minus here and plus here. What do I get when I plug this in? Right, so I have Ci sitting over here. Ci, remember, is a fluctuation in the I spin chemistry, and this is a fluctuation in the, is not an operator. Which two terms have the same sign in both expressions?
That's alpha. I did a mistake.
Alpha alpha minus beta beta. Are the same. Then, if I add up, this is the total. Let's see, if it's any internet, everybody else is on. But that's okay. And which terms are the opposite? Also beta minus beta. What does this Hamiltonian look like? This is a zero quantum. In that case, what do you get for the R2 of the double quantum component? What did you say? Louder.
Due to the square of the sum times the correlation time.
Right. So variance times correlation time. Variance is square of the fluctuation in frequency. So you get something like this. Well, I'm just going to say it goes as this because you will have a bunch of multiplying factors because of the correlation timing of that. Right. So you're going to say it's some arbitrary constant A times the sum of the two fluctuations added and squared, which is important because you're not adding the variances directly. You're not doing Ci squared plus Cs squared. you have an extra 2 CICS carried on. And that is really the crucial aspect of cross-correlated realization of two tensors. If I expand this, you get Ci squared plus Cs squared. And this will be
Same as the square difference.
square of this one. So you get these two are not the same, as you can see. We often define this delta R n Q. This is some of the literature. Delta R n Q is this difference in the R2 of the zero quantum and the W quantum. Just see. For simplicity, we will define it as the model of the sequence. And that in this notation will turn out to be something like 4A, whatever this constant is, CICS times tau C. And you can also write that as eta. Eta is also common symbol for the cross-correlated relaxation of two characteristic terms of each other. Yes.
Not sure it's here, not really.
So trophy for both N15, especially for N15 is the cross-correlated relaxation between the N15 CSA and the N15 proton dipole blockade for N15 itself. Then for proton, it's the cross correlation between the proton CSA and the proton N15 dipole blockade. So those are the two, and for the N15, it's a really strong effect because of the balancing. Because it's very analogous because there's also cross correlated relaxation. But you access it by sort of studying the differential relaxation of the N nitrogen coherence when protons spin up versus when protons spin down. So the two doublet components will be called them. N plus H alpha and N plus H theta. Those are the two. That is going to be real. You can do a very similar treatment as we did in class. To study the difference in R2 of those two doublet components and thereby get a differential line broadening or similarly an eta. That eta is different. This eta is different because it involves the two CSAs cross-correlated. Cross-correlated fluctuation of the N15 CSA and the proton CSA. And you cannot access that unless you create a double quantum horizontal quantum. As far as me. Keeps in R2. Maybe there is some contribution of this cross-correlated relaxation also to trophy, but I'm not too sure about that. Okay, so this was just remember like the first part of the problem, and we already at almost 3:30. The rest of the problem asks you to handle this problem using the NLP approach. And a sort of a formulaic way of doing about things, and you can do that at home. This question is saying whether a particular relaxation pathway is regarded as auto or cross relaxation depends on the operator base. Write a matrix equation for the zero and double quantum coherence using the above results. This problem is basically saying you want to have DDT of double quantum and zero quantum. And you've got these R2s. Right? These R2s are just what we calculated right now. Now the question is there going to be a cross relaxation between these two coherences?
Yeah.
No. One answer, no. Other answers. Will double quantum relax into zero quantum? Zero quantum relax into double quantum. This why no?
This is so. I
That is related, but remember the Renfield kite? What conditions must hold for two terms in the density matrix? And remember, these are all terms in the density matrix. Each of them will have their own weight depending on how you manipulate this thing. Conditions for two coherences or two terms in the density matrix to cross reaction into one.
Inverted frequencies. Right. So the operators must have degenerate frequency with the interaction frame for the cross relaxation to occur.
Essentially. I like to think of it as similar, coherence order, similar, or same idea, but double quantum is coherence order 2. Involves at the sum of the frequencies. Zero quantum is coherence order 0, involves the difference between frequencies. The two don't cross that into one another. But the last part which we haven't done, which I encourage you to do, is write is transform this equation to obtain an equation for the relaxation of XX and YY. So double quantum is described here as plus 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 minus minus, which is XX minus, this is the typo, XX minus YY. And this zero quantum is defined as XX plus YY. So if you look at XX by itself, it's a mixture of zero and double quantum. YY by itself is a mixture of zero and double quantum. So those two, XX and YY, will cross relax with each other. And so if you perform the simple like linear transfer on this matrix to go from double quantum to zero quantum basis, XX and YY basis, you will get a octagonal cross relaxation term, and that will be your. That's one of the most common measurement solution NMR for this CSA cross correlated relaxation. That's how it's done for N15 proton. You create an N15 proton XX, one experiment and a YY, another experiment, and you measure how they cross relax. So we've got time for today. Finishing this problem will be very useful. Any questions before we end?
I have an announcement if we're wrapping up.
Yes.
This is also for people online. So the exam is available and it's on Coursewworks. And you're going to go, we haven't been using that site very enough, but you're going to go there under quizzes and there'll be a place to upload. And the file itself with the problems is under files in a folder that's appropriately named. You have almost 2 weeks. So you're gonna return it not next Tuesday, not this Tuesday, but the fall Tuesday, so that's 12 days from her. Yeah. And, if you are enrolled in a program that's not Columbia University, some other, university, and you're taking this for a grade, and so you need an exam, would you please email Whitney, who has been sending, information about the course in general? Please email her and she will make the exam available to you. Or for the Columbia students, please just go to the coursebooks, it's there. As you know, it's honor code. No time limit. Open books, open notes. And, if you see something that you think might be a typo that's irritating you, don't hesitate to let our company know. So I hope it's not painful. I hope it's somewhat educational. That's it. Should I say anything else about the exam? Did I forget to say something? It's there as of 5 p.m., so not quite yet. If you go there now, you'll see it's there, but you won't be able to access it, so you have to go back to 5 p.m.
Okay, see you next week.
Very good.
When is it due?